So first let's take a look at some of the major components inside of an 8-bit computer. And to do that I'm going to use a diagram that I found in this book, the Z80 Microcomputer Handbook. And we're going to be looking at actually a different book because it's not in this book. This book, Understanding Your ZX81 ROM. No, it's not that book either. What the hell book is it? Hey everyone, welcome back. Today I wanted to take a brief look at the internal architecture of an 8-bit microcomputer, in particular how it relates to the bits and bytes that we discussed in our last episode. We're not going to be taking a too detailed look at all of the internal components of a computer, but I do want to take a look at a couple of the major components as well as the signal lines that connect them. But before we get to that, let's have a little pop quiz on what we discussed in our last video and see if we remember what we learned from that one. Okay, so let's take a look at our pop quiz questions now. Question number 1. What is a bit? Well, if you remember from our last video where we discussed bits and bytes, you'll remember that bit is short for binary digit, which is a digit that can contain one of two possible values being either 0 or 1. Okay, what is a byte? Well, a byte is a collection of 8 bits strung together, with each bit within that byte containing also a possible value of either 0 or 1. So far so good. Now, question number 3. What do you call 4 bits? If we take a byte and split it into 2 equal sections, each of which having 4 bits, we call those nibbles. So a nibble contains 4 bits. Now for our final question. What are the hexadecimal characters? If we remember that hexadecimal is a base 16 counting system, that means that each character must have one of 16 unique possible values. Therefore, we need 16 different characters in order to represent the hexadecimal digits. And those characters range from the digits 0 through 9, as well as the letters A through F. Alright, well done. So first, why don't we take a look at a block diagram of some of the major components inside of an 8-bit computer. And I'm going to use one that I found in this book here, An Introduction to Z80 Machine Code. And we have a diagram on page 8, which I'll show you a close-up of. So here we see on the top left of the diagram, it shows a block labeled microprocessor. And on the top right of the diagram, it shows a block labeled memory, and below that RAM and ROM. And then you see another block labeled input-output devices on the bottom, as well as some other miscellaneous things such as a clock, the address bus, the data bus, the control bus, and some interrupt inputs. Now the main parts of this diagram that we're interested in are the microprocessor, the memory, and later we're going to be discussing the address bus and the data bus. So first let's talk about the microprocessor. So what is the microprocessor? Well, as you probably know, the microprocessor is the main chip or integrated circuit inside the computer that really does all the work for us. It's what controls the computer and allows it to do everything it needs to do, and it is what runs the programs that we're going to be creating. Now the microprocessor that's inside a Sinclair Spectrum computer or the ZX Spectrum Next computer is what's known as the Z80 microprocessor. Now, I should mention that the ZX Spectrum Next computer doesn't actually contain an authentic Z80 microprocessor, but rather a kind of a recreation of a Z80 microprocessor made using a different type of chip known as an FPGA, which stands for Field Programmable Gate Array, which we don't need to know anything about that. But essentially, for our purposes, we can consider that the ZX Spectrum Next computer does contain an actual Z80 microprocessor as far as our programming goes, although it does contain some extra programming commands that hopefully we'll be able to use in our journey at some point. But for the most part, we can just consider that the ZX Spectrum Next contains a Z80 microprocessor as well. So we're going to take a look at the Z80 microprocessor in a bit more detail a bit later on, but first let's discuss the other block, which is memory. So as you probably know, memory is where the computer stores information. And there are two types of memory, and those types are RAM and ROM. Now RAM memory stands for random access memory, and this is memory that you can read and write to, and you can put new values in there and read the old values, and you can manipulate it as you want. Whereas ROM, which stands for read-only memory, can only be read. You can't write new values into read-only memory. So you might be wondering, what is the purpose of having read-only memory inside of a computer to begin with if you can't write to it? If you can only read the data that's already in there, what good is it to us? Well, the ROM memory is very important to the computer because that's where it holds all of the code and the instructions that it needs in order to do its job. So when you first turn on the computer, for example, it needs to know how to function and how to start up. And the ROM memory also includes other routines that the computer needs in order to operate, such as being able to read the keyboard and so forth. And one other important thing about the ROM memory is that it doesn't lose its data when the power is removed from the computer. So when you turn off the computer, all the data that's inside the ROM memory stays there even when the power is removed. Unlike RAM memory, random access memory, which we can write to, and that's where we're going to be storing our programs. However, we do need to bear in mind that any information that is inside the RAM memory will be lost when the power is removed from the computer. So the RAM memory is where we're going to be storing our programs initially when we're writing them. But obviously for longer term storage, we're going to need some other type of media such as the SD card inside the ZX Spectrum Next computer. Okay, so let's go back and take a look at the CPU in a bit more detail now. And I thought it might be interesting to look at my old Timex Sinclair computer, which I have right here. And if we open it up, we find nothing inside. I do have the circuit board though I can show you, which is here. This is an external keyboard that I attached to it as well. But what we're interested to look at here is the circuit board, which has right here the Z80 microprocessor chip on it. So we can see that the Z80 microprocessor is an actual physical chip on the circuit board, and it has pins that are used to connect it to other devices on the circuit board. And now I want to take a look at a diagram showing those pins. So let's take a look at this book, the Z80 Microcomputer Handbook, where on page 27 it shows a diagram of the CPU and its pinouts. So if we take a look at the diagram showing this Z80 microprocessor and the pins connected to it, although this diagram doesn't show the pins in the exact same layout that the pins are physically connected to the chip, it has them grouped by their function, so it's easier for us to understand by looking at it. And if we look at the top left of this diagram, we see a group of pins labeled address bus, and they range from A0 through A15. Now just below that we'll see another group of pins labeled data bus, which are labeled D0 through D7. So what is an address bus and a data bus? So these are physical connections that are connected to the Z80 microprocessor chip inside the computer, and these lines also connect to other chips inside the computer, such as the memory chips. Now, the interesting thing about the address bus and the data bus is that these physical pins, which connect to the CPU and the memory chips, these are the lines that are carrying these voltages we discussed in our last video, where the voltages can be either 0 volts or plus 5 volts, which relates directly to bits and bytes, which have two values of being either 0 or 1. So when we're doing our programming and we're using bits and bytes that have two values, either 0 or 1, those bits and byte values refer directly to the signals that are on these address bus pins and the data bus pins. Now we discussed memory a bit earlier on in the video, and we talked about RAM memory and ROM memory, but we didn't go into too much detail about how the memory works exactly. So there are a couple things that will be important to us in our programming that we need to understand about memory. And those two things are basically address and data. So as we just saw on the microprocessor chip, it has address lines and data lines. And the purpose of these two buses, the address bus and the data bus, is to indicate where in memory a piece of data is stored, and to indicate what that piece of data actually is. So for example, the address lines, as we know, now will contain digital values of either 0 volts or plus 5 volts, and those values relate directly to the values of bits and bytes that we'll be using in our programming. So by changing the values of the address bits, we can determine which particular memory location we're interested in looking at. And we use this either to read the value of a piece of data that's in that memory location, or to write a new piece of data into that location. So this happens inside the computer, but we control it by using our programming, indicating the particular memory location we're interested in by manipulating the bits and bytes of the address lines. Now the data bus is what indicates what piece of data will be stored in a particular memory location. Now the data bus inside the computer also carries voltages on each pin of either 0 volts or plus 5 volts, which we now know relates directly to the bits and bytes that we're using in our programming. So 0 volts relates to a 0 and plus 5 volts relates to a 1. And these are the bit values that we talked about last time. And in an 8-bit computer, typically there are 16 address lines, which allow us to have 65,536 unique address locations, and 8 data lines, which allow a possible data value ranging from 0 in decimal to 255 in decimal, which, as we should know by now since we covered hexadecimal in our last video, ranges from 00 hexadecimal to FF hexadecimal. And if that's confusing to you, you might want to go back and rewatch the last video where we talked about hexadecimal and how to count using hexadecimal characters. Now, one other interesting thing to note is that 8-bit microcomputers are referred to as 8-bit computers because they contain an 8-bit data bus. The data bus has 8 physical lines connected to the CPU and to the memory, so those 8 data lines in the data bus is what gives an 8-bit microcomputer its name. Now, I'm sure we all finished the homework assignments that were given out in our last video, so we'll go ahead and take a look at the solutions now. Okay, so let's go ahead and take a look at our homework assignment from our last video. Now, assignment number 1, we had to convert some binary byte values into their equivalent decimal values. Now remember, in order to do this, all we need to do is convert each individual binary bit into its equivalent decimal values and then add those together to get our value for the entire byte. Now in the first question at the top here, we only have one single bit which is turned on, and it is the one on the far left hand side, which hopefully we all remember is referred to as the most significant bit because it has the highest decimal value, which in this case would be 128. So in this case, the value of the entire byte would therefore be 128 because there's only one bit actively turned on. Now for our second question, we have every alternate bit is turned on. And so for this one, we need to do a bit more work. We need to actually convert the decimal values of each bit so that we can add them together and get the value of the entire byte. And if we do that, we come up with these values, which are 128 plus 32 plus 8 plus 2, which gives us a total value of 170. Okay, so now for question number 3, we can see in this byte we have 2 bits turned on, the most significant bit on the far left and the least significant bit, which is on the far right. Well, we already know that the most significant bit has a value of 128 from question number 1 of this exercise, and we should remember that the least significant bit has a value of 1. So the answer to this one should involve adding 128 plus 1, which it does, which gives us a total value, of course, of 129. All right, now for our fourth and final question in this assignment, we have all of the bits turned on. So this one should be an easy one to figure out because we should automatically remember the total value of a byte with all of the bits turned on is all of the bit values combined together, which gives us a total of 255. So this is one of those values that it's just useful to remember without having to look it up or add up the individual bits. All of the bits turned on in an 8-bit byte like this would give us a total decimal value of 255, and so that's something that we should try and remember. Now let's take a look at assignment number 2. In this assignment we have some hexadecimal values that we need to convert into their equivalent decimal and binary values. So these hexadecimal values, as you can see, consist of 2 digits, and if we remember from our previous video, each hexadecimal digit is equivalent to 4 binary bits, which can have a possible value of decimal 0 through to decimal 15. So first of all, let's convert these hexadecimal values into their equivalent decimal values. And the easiest way to do that is to remember that hexadecimal is a base 16 counting system, so each digit can have one of 16 possible values. And let's start with the digit on the left. And we need to remember that the digit on the left represents multiples of 16, since hexadecimal is a base 16 counting system. So for the first example here, we have 0f, and we take the leftmost digit, which is 0, and that gives us 0 multiples of 16, which of course equals 0. So we take 0 times 16, which is 0, and we add to that the other character, which is f, which we should remember equals a value of 15 in decimal. So if we add 0 to 15, of course we get a total value in decimal of 15. Now let's go down to our next question, which is a hexadecimal value of 20. So again, let's start with the leftmost digit, which has a value of 2. So we know that there are 2 multiples of 16, which gives us 32. And to that, we need to add the rightmost digit, which in this case has a value of 0. So 2 times 16 is 32 plus 0, giving us a total value of 32. Now for question number 3, we have a similar looking number, which is 30 in hexadecimal. So in this case, we have 3 multiples of 16, and to that we add 0. So 3 times 16 gives us 48. So now we have 3 times 16, which is 48, plus 0, which gives us a total value, of course, of 48. Now in hexadecimal, we have FF, which we should remember that F is the maximum value of a hexadecimal digit, which can be 15, since it's a base 16 counting system. So here we have F multiples of 16, and F, as we know, represents the number 15. So in this case, we have 15 multiples of 16, which gives us a total value of 240 in decimal. But now we still have to add, of course, the rightmost digit, which is F, which we know has a value of 15 as well. So we have our 15 multiples of 16, which equals 240, and to that we add our second F, which has a value of 15. So 240 plus 15 equals 255. And this again is the value that we should remember from our previous slide, because this, as we know, equals all of the bits in a byte turned on, which is kind of a spoiler alert now to the binary equivalent value of this question. So we'll just move on and go back to figuring out the binary values starting from the top. So we'll go back to the hexadecimal value 0f and convert that to binary. Now the easiest way to convert hexadecimal values into binary values, in my opinion, is to convert them to nibbles, which are 4-bit values. So if we take each hexadecimal character and figure that out individually, in the first example where we have 0f, first let's take a look at the leftmost character of 0. And what equivalent binary nibble value would equal 0? Well, of course, that would be all of the bits turned off, which would give us a binary value of 0000. Now let's take a look at the f in that question. F has a decimal value, as we know, of 15, and in order to get 15, that is the maximum value of the bits that can be represented in a nibble. So if we have all of the bits turned on, that will give us the maximum value of 15. So in this case, the binary byte value would be 00001111. Okay, now let's take a look at question number 2, hexadecimal 20. Again, we'll take a look at the leftmost character, which is 2, and what nibble value or 4-bit value would give us a hexadecimal value of 2. Now this question might seem a bit confusing, because now that we're splitting up these hexadecimal character pairs into their individual characters, you might wonder, does that 2 represent 2 multiples of 16, or does it represent a decimal 2? Since we're splitting up these hexadecimal pairs into their individual characters to convert them to nibbles, we will no longer treat them as multiples of 16 in order to convert them to their binary nibbles, but just as their individual values on their own. So in this case, that 2 character would convert to 0010, because as we know, the 1, which is the second least significant bit, would have a value of 2. And of course, the 0 to the right of that in the hexadecimal characters 20 would have a value of 0 as well, giving us a total byte value in this case of 00100000. All right, now question number 3 is very similar. Again, it is 30 in hexadecimal. So again, we're going to take that 3 and convert it to a nibble. And in order to get a 3 in a binary nibble, we need to have 2 bits turned on, the least significant bit, which represents a value of 1, and the one right next to it, which represents a value of 2. So a hexadecimal value of 3, which is also a decimal value of 3 for that individual character, would give us a binary nibble value of 0011. And of course, this question also has a 0 as its rightmost hexadecimal character, which gives us a binary nibble value of 0 as well. And when we combine that with our 3 that we had on the left-hand side, we have an entire byte value of 00110000. Okay, now let's take a look at our fourth and final question in this assignment, which is hexadecimal FF. And now we know that each F represents a decimal value of 15, which also means all of the bits are turned on. So this should be very easy for us. All we have to do is turn on all of the bits in each nibble. So the leftmost nibble here will turn on all of the bits, giving us 4 ones, and we'll do exactly the same thing to our rightmost nibble, giving us another grouping of 4 ones. And when we combine those together, we get a byte with its maximum value of 11111111, which now we can see has a decimal value of 255, and that equates to our hexadecimal value of FF. Okay, great. So we have one more assignment to go here, and let's take a look at it. Remember, now we wanted to take a look at a 2-byte value in this exercise and see how we could convert the individual bits in a high byte of a 2-byte value to its equivalent decimal values. So this is a very easy problem to solve. Again, all we have to do is continue doubling all the decimal values as we've done here in our rightmost low byte. We've gone from 1 to 2 to 4 to 8 to 16, 32, 64, and 128. So now all we need to do is continue on with that pattern and double our 128, which gives us 256. So let's just expand this a little bit so we can see it a bit better. And we'll just focus on the high byte now. So let's go ahead and continue doubling these decimal values over to the left-hand side, which would give us a next value of 512, and then 1024, 2048, 4096, 8192, 16384, and 32768. So you might be wondering, do I really need to memorize all these values of a high byte because they're kind of complicated and difficult to remember and difficult to do calculations with, numbers that are getting into this kind of high range? The answer is no, we don't. What is useful for us to understand about the high byte, though, is this next thing we're going to take a look at, and that is what would be the value of the next bit in this series. So if we were to expand into a 3rd byte now, and we kept doubling these decimal values, you can see our next bit to the left would have a value of 32,768 multiplied by 2. Now, of course, that would take us out of these 2 bytes and bring us into yet a 3rd byte. And the reason this is important and interesting for us to know is because once we figure out what the value of that next bit would be, which is in this case 65536, we know automatically that if we take all of the bits combined in these 2 individual bytes, which contain 16 individual bits, we know that if we add all of those 2 together, they must give us a maximum decimal value of 65535. And the reason we know this is because the value of the next bit is 1 higher than that, which is 65536. So automatically we can calculate the value both of the next bit over to the left if we know the value of all the bits to the right of it, or we can go backwards, and if we know the value of the leftmost bit, which in this case would be 65536, we know that the value of all the bits combined to the right of that, in this case, which would be 2 entire bytes, would have a maximum value of 65535. So we know from looking at this that 2 bytes, which is 16 bits, can have 65,536 possible unique values ranging from decimal 0 through decimal 65535. Now for our bonus challenge. In this exercise, we were supposed to create a spreadsheet that automatically calculates the decimal value of a binary byte. So what I've done here is I've made an entry for each individual bit value, which will be either 0 or 1, And then below that, I've manually entered the equivalent decimal values for each individual bit. Then below that, we have a formula which automatically multiplies the bit values by their equivalent decimal values. So if the bit is turned on, or has a value of 1, the result will be its equivalent decimal value. However, if the bit is turned off, or has a value of 0, then the result will also be 0. And here we have a formula which simply adds together all of the equivalent decimal bit values, giving us the total decimal value for the entire byte. Well, that wasn't too difficult. How does that compare with your solution? So, thanks for watching. Hopefully everything that we discussed today made sense and the internal architecture of computers is a little demystified now, and we understand more about the different components that are inside there and how they relate to the bits and bytes that we discussed in our last video, because there is a direct relationship between the bits and bytes and the signals inside the computer, as we now know. So hopefully that all made sense to you. And if you have any questions or anything is not clear, feel free to go back and watch the previous video, or if you like, you can also leave a question or comment down below. So thanks for watching this video, and just a reminder, if you would like to help support this channel by becoming a Patreon subscriber, feel free to head over to patreon.com/SpriteWorks, where you can check out the different subscription levels. Thanks again, and we'll see you next time.